Okay, I have a lot to clarify. So a lot of questions that I did were very incorrectly solved because I didn't have enough knowledge of this subject, right? Yeah, so 299, that is incorrect. And 297, I think it was not incorrect, except that 299 is, because in 29, okay, just first of all, see what 297 was. Solid copper cylinder of length something placed on a horizontal surface and subjected to vertical compressive force directed on downward and distributed uniformly over the end face. What will be the resulting change of the volume of the cylinder in cubic millimeters? So right, that was this thing, sure. Yeah, I mean, that whole derivation was correct. No big deal with that. Then the problem is that like after that, yeah, there was something else that I had to account for, but I didn't. Anyway, I'll explain it now. So 298, what was the question? Right, okay, this was not so different. And increment of the volume. Yeah, okay, this is also pretty much the same stuff. You don't have to worry about that. Except that it should actually have one minus 2 mu because it's like those lengths are actually decreasing, right? The lateral strain is negative, right? So it should actually be 1 minus 2 mu. Otherwise, it was all correct. So not, I mean, right, not that big of a problem over here, except this should be 1 minus 2 mu. Okay. The problem is with 299. So a bar made of material whose Young's modulus is equal to E, Y, and Poisson's ratio is equal to mu is subjected to the hydrostatic pressure P. Find the fractional decrease in its volume and the relationship between compressibility and the elastic constants E and mu. Right. So the thing I did was that I just took one surface. So we got this block, I don't know, it's a cube or whatever it is. Okay. I just took one surface, maybe the top and bottom one, right? Okay, I meant two surfaces, opposite surfaces. So I just took this one and then I did the thing, right? So the stress over there is equal to the strain times the Young's modulus. You get the thing, right? I did that, and yeah, that's how I got this relation, which is completely incorrect because the thing is you also have to account for the stresses from the other direction because Poisson's ratio, right? It's going to cause changes in your strain in a particular direction. So across x-axis, this is like the x-axis, then you also have to account for the pressure along y and z-axis because those also matter. So this is not the real thing. This is not how it should be. Instead, you will have to use this thing. So this is called the, I don't know, is it the general Hooke's law? No. General Hooke's law also accounts for shear stresses, but yeah, it's pretty much a general Hooke's law for this particular case because no shear stresses. So yeah, so it's Ex, Ey, Ez, which are the strains in x, y, z directions. Those are just equal to. So you will have 1 minus mu, then you got minus mu 1 minus mu, then minus mu 1. All right, all of that. Okay, wait, I should also have this 1 upon Young's modulus. And then you got the stresses. So, right, stress, which is, let's just call it sigma. So sigma x, sigma y, sigma z, right? So in this particular case, all of these are actually the same. So like they are the same as the pressure P. So this whole thing, right, it just becomes 1 upon the Young's modulus, and then you just have, yeah, you got sigma times 1 minus, okay, P basically, because that is just that. So P times 1 minus 2 mu, then once again P times 1 minus 2 mu, and P times 1 minus 2 mu. So, right, this is our strain vector, I think. Yeah, so it's just equal to Ex, Ey, Ez. So as you can see, all of these values, Ex, Ey, Z, are the same values, and they're just equal to what? The pressure upon Young's modulus times 1 minus 2 mu. And then dV upon V is just equal to 3 times of, okay, I should not say that. It's just equal to dx upon x plus dy upon y plus dz upon z, right? Yeah, I mean, is that so hard to understand? V equal to x, y, z, just apply natural log on both sides and then differentiate. Yeah, you know the thing. You know the thing. So what that means is our volumetric strain, that will just, oh, and by the way, I'm saying P, it should actually be negative P because yeah, the stress that I'm talking about over here is actually uh, corresponding to elongation. So it's tensile stress, but the pressure is actually compressive, so it should be negative P. And that would be the correct thing. So, right, that's the thing. And also these, right, okay, these are in fact tensile strains, so no big deal with that. So like dV upon V is just equal to -3 of this thing. So yeah, so of course, I mean, that just means like the volumetric strain is compressive, which is obvious because pressure is there, right? So this strain, well, divide the stress by the strain, you will get the bulk modulus, right? So our stress is just this thing. Okay, what am I doing? P upon -3 upon Young's modulus, and you got 1 minus 2 mu. Right, this is just equal to bulk modulus. Not quite, not quite, because it should actually be negative of that thing. Yeah, yeah, right, like the stress that is negative P. Does that make sense? Okay, so that's our bulk modulus is just equal to what? Oh, sorry, it should be 3P over there. So like this is just equal to what? It's equal to Young's modulus upon 3 times of 1 minus 2 mu. So what does that mean? That just means the Young's modulus equal to 3 times the bulk modulus times 1 minus 2 mu. That's what I wanted to show. So yeah, you got the relationship between compressibility or the bulk modulus or whatever, and the elastic constants, this and that. Cool, I got the thing. So this is wrong. It's not correct. Instead, you should have this relation. Young's modulus is just equal to 3 times the bulk modulus times 1 minus 2 mu. Right. And if you want to learn this in detail, not that much of detail, not more than necessary, then go check out this video that I just published. Not just okay, maybe I did this 2 days ago, I don't know. So watch that video. What was it called? I don't remember the thing. Oh yeah, elastic modulus. Yeah, that's the title. Just watch that video. You will understand what this thing is and why am I using this thing. It has to do with superposition of strains. So yeah, you will understand that. Anyway, that's done. And so in the last video, I even commented that this should have been G, this should not have been capital Y. But yeah, like unfortunately got capital Y over there, right? So I mean, I wrote it at first, I didn't understand what was I doing, and then I just repeated writing that. So it should have been capital G. But even after that, this is actually incorrect. But yeah. So why is this happening? So throughout the thing, like I just consider the, what do we call it? I mean, it may not be actually wrong. Who knows, right? It might not be wrong, but this was not what the question was asking. So I got this thing as our what was the thing once again? Right, our radius of curvature, right? So at x equal to 0, this would just become what? This, okay, 1 plus, yeah, just that thing. Times of 3g upon Young's modulus squared, and then you got 3.2. Right, now, okay, that's why I hate this. So this is actually not good. So like it involves y dash and whatnot. This thing is related to y dash, right? We saw that in the last video. Yeah, right. But the thing is that y dash, we assume that to be like, oh god, no, okay, I think I messed up some. X equal to L, that's where we should have done, oh right. So it should have been x equal to L. So when that happens, this is actually 0 itself. So right, I don't have to worry about that anymore. But even if it was not x equal to L, it was any kind of x, this thing would still be small. That's the important part, that this is actually for small deflections only, right? Only for small deflections can you use whatever equations you want to use. So according to that, this should be small, and then you would say, okay, like G upon this, okay, that's the thing, right? Well, no, there's a very big problem in my derivation. The last time I did this, I took the strain, the shear strain to be equal to the slope, which is a very bad thing to do uh, because I mean, think about it. You have this deformed horizontal bar, and so like before deformation, you might have this part, right? Yeah, this part might be like this actually. So after deformation, if I just rotate it, like I just rotate everything else, and then this falls in place, then this would be like so, right? But the thing is, like, there is shear stress, so it's actually not like that. Right, instead it's like, oh god, how do I explain this? It has some force in this direction and whatnot. So yeah, you get the thing. It's just going to shear. This is so hard to explain. Maybe I should use a different geometry. So like this might be the thing. So then over here I should have this as the initial part. So this is the part that will be rotated to get this thing, and then you have a shearing. So right, it's not just the slope. The slope is, if you just rotated it and you saw this, right, that would be the slope. But that's not the thing. You have another small gamma thing over here, and that's what's causing the shearing, right? So it's not just the slope. It's the, how do I explain this? After the rotation, if you don't shear, you will get the slope. If you shear, you don't get the slope. For this surface, I mean, the slope is not the same as what it was before. Does that make sense? So that thing gamma equal to dy upon dx, that is not correct, right? You should not do that. I repeat, you should not do that. Instead, the correct way of doing this is actually a very complicated way. You should watch that other video where I described how deformations happen in rods, right? Or bars. Actually, it's not rods, because for rods you would have a different aerial inertia. Okay, I'm getting too deep into the details. So the equation that you would be using is this thing. We just have the tau, which is, okay, I'll explain what it is, but first just write down. And then you got the Young's modulus, then the aerial inertia, which might sound like, what is this? But it is something, trust me. And then this upon the radius of curvature. So this equation you can use for this question, and you don't have these equations anymore because those are just wrong. So no, you don't use those equations. And 301 we are not doing right now, we're just doing 300. Okay. So let me explain what these things are. You got this rod. Okay, we know it's going to like do this or whatever, and it's supposed to be small deflections, but then whatever, we don't have to think about. Okay, yeah, I mean, just exaggerated figures. Okay, tau, it's the torque exerted by one side of uh, of this bar, okay, of this what is this thing once again, of this beam on the other part, right? So you know there's gravity and everything, so it's like, yeah, with respect to this point, this gravity is creating a torque, right? So you want something that will cancel that torque. But what is there? What kind of force is there that will cancel the torque? There's this shear force on this that will cancel the force itself, but then, yeah, like it's not exactly creating any kind of torque because it's at the point itself. So like taking this as the origin or whatever. Yeah, so the torque is still there. It's not getting cancelled. So then how would we do that? The thing is, you have to think of it not as a single point, but actually as kind of like a cross section. So this is how it should be. I know this should be rotated, but then think about it just like rotating after you get the thing, right? So yeah, it's supposed to be rotated, but just do it. Okay, so this torque is in clockwise sense. You want an anti-clockwise torque on this piece, right? The way this will actually work is that you will have these normal forces, right, which will cancel out, like they will add up to zero because no horizontal force is there actually, but they will create a torque about this point. So because of that, right, because of that, you will have like, what do I call it? You will have cancellation of torques, and this won't rotate. Okay, now That torque is this thing. And let's explain what this thing is. You already know what Young's modulus is. This R, it's the radius of curvature of this point. Okay, so yeah, and then 1 upon R would just be like y double dash upon 1 plus y dash power 3 upon 2. You get the thing, but we don't actually care about that right now because we have been asked to find the radius of curvature itself. So you don't care about that expression really. And yeah, I mean, I actually derived the whole equation. So like, what kind of curve is this? I derived it. You can watch that video. You will understand what we are doing with this equation. But we don't care about that right now. We just care about what this 1 upon R value is at x equal to 0, right? So at this point, what will this be? And now this thing, what is this going to be? It's integration of y square dy or z square dy, or whatever you want, right? But what's y, by the way? Y is just this thing or this thing, doesn't matter. Okay, so it's this thing throughout this throughout this surface. So the cross section itself, if you just think of the cross section, so like it's rotated by 90 degree first of all, and then I'll take this point of view. So this is our TA element on this cross section, and then this thing is y for that. So you just do this integration over this whole surface, and then you will get this IA value. This is called the aerial inertia. I don't know why they are doing this, like, but fine. This term comes in our calculations, so might as well use this thing. Okay. So our question, where did I go? 300. So one end of a steel rectangular girder is embedded in a wall and it's a rectangular girder. Fine. Due to gravity, it sags slightly. Find the radius of the curvature of neutral layer. See the dotted line in the figure in the vicinity of point O. Okay. If the length of the protruding section of the girder is equal to L and the thickness of the girder equals to H. So yes, that's actually sufficient to figure this out. Right. It's not square. That's a problematic thing. You will have to like, oh yeah, that will be a problematic thing. But fine, we can do this. It's not that bad, I guess. Right. Right. I guess so. Okay, let's just try it out. So by the end of the derivation, you will be able to express everything using density, Young's modulus, and these dimensions, right? So that's what we need. Now, for a rectangular cross section, let's just say of, I don't know, of well, they already gave us the height. So this is H, and this dimension is called it like W. So you got this thing, and this is our y equal to 0 line. You want this thing, like this is just going to be equal to integration of, just take these strips. They have the same y square dA values throughout, right? So just take these strips. The dA for this thing would just be like W dy, and then you got y square. So integration of this thing from negative h upon 2 to h upon 2, right? This thing is just going to be what? It's like W h cube upon 3, but 2 times of that. So 2 upon 3, and then you got h upon 2 cubed, right? So like y cubed, sorry. So yeah, h upon 2 cubed, which is just h cube upon 8. So this will just be W h cube upon, so this is like 4, I think. It's just 4. So 12, right? That's what this value is. So you can write this equation once again. Tau is just equal to the Young's modulus we know. IA is this thing, WH cube upon 12, right? This is supposed to be 12, sorry. Well, yeah, sure. And what else? Upon R. So that's the thing. Now we will have to figure out what the torque is about this point, right? Of this complete system. So this is like the total mass of this guy. So mg force, but at this point, so it's like L upon 2, just mg L upon 2. That's our torque about that point, right? Yeah. Yes, I think that's correct. Okay, and now m is not something that we want. Instead, we will actually try to write this using density. Did they give us what M is? No, they did give us it's made of steel, and you can figure out the density of steel. It's probably given in their appendix, but we won't we won't actually look up that value. We'll say it's equal to what? Rho times L times W times H, and then that times of GL upon 2 second squared, and then you got GL upon that upon 2. Just put that into this equation. So this is just equal to what? This thing. Cool. So then some stuff cancels, just like this cancels, this cancels, just square root it. So rho L squared G, 6 times of actually 6, and that's also R over it. That is equal to the Young's modulus times WH squared. Oh, sorry, W got cancelled. Why didn't I cancel this? Okay, just equal to H squared. Right. So our radius of curvature is just equal to the Young's modulus times H squared upon this thing, 6 rho G L squared. All right. Yeah, that looks about right. So dimension analysis, this thing is like pressure times area, because yeah, Young's modulus is just units of stress, which is also like pressure. So pressure times area, just force. This thing is force. This thing is wait, 6 rho GL would be pressure. Like it's just pressure times length. So pressure times length squared upon pressure times length. It's just length, right? So dimensionally, this looks correct. And I think that is in fact our answer, right? So you got the radius of curvature at x equal to 0. Cool. So that's our answer. Next question. You won't believe where I had to go to actually learn all of this. It's like there's a whole playlist about this kind of thing, right? Yeah, I watched that and it did help me, but in the end I had to derive by myself, because to actually get understanding of what I'm doing, when should I use this equation, for what should I use this equation, I have to derive it by myself. Yeah. Now 301, that's the next question. Quick. Oh, okay. Sorry. Okay, 301. The bending of an elastic rod is described by the elastic curve. So yeah, now they are telling us what to do. And the way they are describing this, you won't ever be able to understand what's actually going on. But now we do. Okay, of an elastic rod is described by an elastic curve passing through the center of gravity of rod's cross section. Yeah, like this thing, right? Okay. Yeah. At small bending, the equation of this curve takes. Oh, and by the way, all of this stuff that I did, I forgot to mention that for all of this stuff to be correct, your h should be much less than L, and W can be anything. We don't care about that, but your h must be much less than L, right? Okay. Now let's go to 301. Bending of the elastic curve is given by this expression. Okay, whatever. At small bendings, the equation of the curve takes this form. Yes, where nx is the bending moment of elastic forces in the cross section corresponding to the x coordinate. E is the Young's modulus. I is the moment of inertia of the cross section related to the axis passing through. I know this, all right. Suppose one end of a steel rod of a square cross section with side A is embedded into a wall, the protruding section being this much. Assuming the mass of the rod to be negligible, find the shape of, so this rod is light. Oh, that's a different scenario than this one. Assuming the mass of rod to be negligible, find the shape of the elastic curve and the deflection of the rod if its end A experiences the bending moment of couple and not. What? I think all that's saying like, okay, so A experiences a torque basically, right? So like, yeah, maybe like you have, right, I get what's happening. There's something on which A is producing this much of torque, right? If that happens, then yeah, you have to figure out the shape of the elastic curve. And B, a force F oriented along the y-axis. Huh. So there's this force. So okay, there's like strain and whatnot. So okay, I get both of the curves are going to be different. But how? Oh yeah, so like if there's a force like this, F times R will be the torque at this point. Okay, F times this length. Doesn't that make sense? That's the that's the torque because of this force, and then you have to oppose that. So of course both will be very different. So for A, our torque is actually constant because wherever you go, there's only one constant torque, right? So at this point, the torque is just this much. You have to oppose that. This point, the torque is that much. You have to oppose that, of course. So that torque is just constant. And at this, so for B, it's not constant, it actually changes. Fine, we can do this, no big deal. Let's do it. So A, once again, our equation is torque is equal to, oh, and what is this, by the way? What kind of shape is this? Right? What is the cross section? Okay, square cross section with side A. Oh, that's interesting. Huh. Well, yeah. What was the thing? It was just WH cube upon 12. That's our IA value. That's what we got the last time, right? Yes. So in this case, W and H both are the same, which is equal to A. So this is just equal to A power 4 upon 12. Okay, awesome. So you got A power 4 upon 12 times the Young's modulus, and then you got 1 upon R. And 1 upon R is basically just equal to Y double dot in this case. Although that's not quite correct, but yeah, approximate. So that's right. So that now you got this thing. Okay, so they for A they are saying our tau is actually constant, is equal to tau naught. So we just have Y double dot is equal to 12 tau naught upon this constant. Yeah, I mean it's just a constant. So and let me guess, it's going to be this thing. Why do I do this, right? Why did yeah, because the constants are going to be 0. Like y dash is 0 at this point, and y is also 0 at this point. So I think it's good enough. Yeah, this is a solution. It is in fact the solution, right? So this guy's second derivative is just 12 t naught upon y a power 4, and it satisfies all the boundary conditions. So there we go. That's the thing. So you want the bending moment. Sorry, you want what? Find the shape of it. Right, that's it. That's the shape. You got a curve for the shape. So that's just perfect. A is this thing. And once again, you should actually just have tau. Now for B, so suppose you're at X, then the thing ahead of it is like L minus X, right? Oh, it's gonna get complicated actually, but whatever. I think we should use density and not mass to express everything. Yeah. Hey, what did they actually give us? They gave us L, A, and lambda. What? Oh, so why did they use lambda? They didn't use Young's modulus though. Okay, that you just have to. So it's a steel rod. You already know what this thing is. So then what is not known? And for A, they also actually gave us N naught value or T naught or whatever. So why do we even need lambda in that case? I don't know. I'll probably not do that. So A, you get the thing. Now for B, it's to B, right? A force F oriented along, initially figure out what lambda is, because maybe they will use that later on. So this is at X equal to L, right? So just 6, yeah, this thing. Then you got L power 2 upon Young's modulus A power 4. Okay, awesome. Okay, then you got a force F oriented along the y-axis. So our, yeah, this thing is just going to be what? We don't need the density at all because it's like a light mass, right? That's the rod is just light. So sure, it's at X. You got L minus X of this thing. So L minus X times the force. Yep, you got the thing. So that's our equation. What if I used a different X value? Well, no, okay, just leave it like that. We don't want to go ahead. So y double dash is just equal to what? 12 f upon Young's modulus a power 4, and then you got L minus X. Now I just want to integrate this. Like y dash is just equal to 12 f upon Young's modulus a power 4. and the delta, okay, integrate that, right? So like you got 6f upon all that, and then you got L minus x squared as it goes from x equal to 0 to x equal to something, x equal to x. Yeah, x equal to 0 is just L. So, and then it's like a negative as well. So it's actually supposed to be this thing, L squared minus L minus x squared. Okay, and then integrated once again. It's like y is just equal to 6f upon this part. This is taking forever. L squared x minus, yeah, I think I saw that somewhere. Have I seen this before? Probably, yeah. It's a cube. Okay. Oh, okay. I saw something similar for that massive rod case, right? It was L minus x squared, I think, in that one. Whatever. Just do it. So it's L minus x cube upon 3. Okay. Yeah, and then as it goes from what to what? From x equal to 0, it's like L to, and also there's a negative such as plus L minus x cube upon 3, and then just goes from 0 to L. So at L, oh sorry, 0 to x. At x will just be this thing. At 0, it will be this. Awesome. So y is just equal to f upon Young's modulus a power 4, and then you got all of this. 6L squared x plus 2 times of L minus x. Actually, you know what? I should have left that 2 outside. So this would be 2f upon Young's modulus a power 4, and then you got 3L squared x plus L minus x cubed minus L cubed. Awesome. Now let's simplify this. So it's got like 2f upon y a power 4, and then this y is different than that y, by the way. Okay. This thing, yeah. L cube minus 3L squared x plus 3L x squared minus x cubed, and that thing minus L cubed, so this is that. Now 3L squared x, I've seen that somewhere, right? This thing, look at that. This just cancels. So it's just this thing. It's x cubed, sorry. 3L x squared minus x cubed, which can be thought of like 3L minus x times of x squared. Awesome. So it's just equal to that. Like it's just equal to 2f upon y a power 4, and then you got this thing x squared times 3L minus x. That's our y value. Oops. Yeah. Uh-oh, I think I should not. Where did the torque equation go? Oh, I just erased that, didn't I? Fine, whatever. This is really all we need. We don't need a torque equation. All we actually need is this thing. IA is equal to WH cube upon 12. This is kind of an important result, I think, because I've used this 2 times by now. So I'm gonna remember this forever, I think. Well, yeah. So you got y. What is lambda going to be? So at x is equal to L, right? Just put that in there. You will get the maximum deflection, hopefully. It's 2f upon y a power 4, and then you got L squared times 2L. So like, interesting. Something's kind of weird over there. It's like a cube. Why is there a cube over here? Is this even dimensionally correct, first of all? I mean, okay, that's square square cancels, and you got like what? It's the 1 upon length. Now, y times length, not exactly what I want. I'll just cancel that away. Now, okay, it's all right. So, f upon y a squared, that's just unitless because y squared is just force. So this is like x squared upon a squared times tail minus x, which is, yes, it's just length. So this is actually awesome. Now put x is equal to L in there. So you got 4 FL cube upon Young's modulus a power 4. Okay, so these are done. Next, 302. 302 is, come on. A steel girder of length L rests freely on two supports. 1.77. It's not. Oh, like this. Okay, the moment of inertia of the cross section is equal to I. Fine. Neglecting the mass of girder and assuming the sagging to be slight, find the deflection due to force F applied to the middle of the girder. Uh-oh. Okay, this is getting complicated, isn't it? Well, yeah. So how do we set up our coordinate system? Let's just set, let's just make this our origin, right? Should we do that? Should we make this our origin? Maybe. Well, first thing, by this force analysis, you can see that these two forces must be F upon 2 and F upon 2 in that direction because no net torque induced. What am I saying? Why am I saying induced? No net torque on this thing, right? That's the thing. And there's like gravity as well, but do we have to consider that? No, I don't think so. Uh, Negative mass of the girder, of course. So neglect that and it's like it's force. You got F upon 2 over there. F upon 2 over there. Cool. Yeah, you know what? No, let's just set this as our origin and set this downward axis as our y-axis as always. Right. So then, once again, the same thing, torque is just equal to what was the thing? Y. And what is this? A rectangular cross section? Where did that go? It is I. Oh, you don't even had. Oh, wow. That is awesome. So we don't have to calculate that, just equal to I itself. Fine, just equal to yi and then y double dash. That makes sense? Okay, now we will have to figure out what this torque is at x. So it's this force. How much is this thing remaining? Oh god, I really have to do this thing. So this is our force in this direction. We got this as x. This is just equal to L upon 2 minus x. This thing is equal to L upon 2. Now it's complete combined is L upon 2 plus x, right? So from here to here it's L upon 2 plus x. Oh no, sorry. It's L minus x. Sorry for that. And over here you got F upon 2. So the torque is how much? We only care about the magnitude anyway, right? And we know y is actually, so y dash is like increasing at this point because, oh no, it's not increasing at that point. Is it? No, at this point it will be 0. And at this point it was like something positive, I would say, because y was increasing, right? So it's actually decreasing in the first half. So it should be negative. Well, whatever. We'll figure that out later. Okay. So we got f times of L upon 2 minus x minus f upon 2 times L minus x is the thing, I guess so. F times this minus that, so negative L upon 2. Oh, isn't that just awesome? This cancels. Oh, sorry, that's F upon 2 over there. What am I doing? F times of L upon 2 minus x minus L upon 2 plus x upon 2. This cancels, it's just that. So negative f x upon 2. That makes sense, negative, because this is going to be negative, right? Yeah. There we go. That's our tau. So negative f x upon 2. Or you just say negative f upon 2x. So negative f upon 2 Young's modulus inertia times x, that's just equal to our y double dash. This is going to be easy, I guess. Yeah, right. Yeah, I think so. So, I mean, of course, it's supposed to be, right? Well, yeah. So like at this point, this torque will be 0, right? Which is obvious because that's what we have always been doing for rigid bodies. And yeah, it's, let's just say almost rigid, not exactly rigid, right? Okay. I mean, at least at equilibrium, it's rigid, right? Okay. So that means we got this equation. Uh-oh. So like y dash is just equal to negative f upon 4 Young's modulus inertia times x squared. Because, it's not, sorry, it's not. Oh god, this is not going good. Uh-oh. I didn't expect this to happen, unfortunately. Y dash is not 0 now. Oh god. And now y dash is not 0. Can you believe that? That is y is 0 at that point. So it's this thing plus some constant. Fine, no big deal. Uh, so at x is equal to L upon 2, it will be 0, right? So put that in there. So you got C is equal to, oh god, it's going to take forever, FL squared upon 16 Young's modulus inertia. Just put that in there. Awesome. Now integrate this. So y is just equal to negative f upon 4 Young's modulus inertia. X upon 3 should be 12 over there. Okay. It's cubed. You got FL squared upon 12 Young's modulus inertia. And x equal to 0 is going to be 0. That's why there's no constant. So there you go. You got the equation. Factor out some stuff first of all. Wow, somehow this was, oh, this matched. Interesting. Are we sure it's supposed to match? Why is it 12 over there? Oh, shit. It should be 16. It should be 16 over here. Oh, yeah, so that at x equal to L upon 2, it's going to be 0. Right, now it is going to work out. There you go. That's the whole thing. So f upon, let's just take out 4, then Young's modulus inertia. Then you got negative x cube upon 3 plus L squared. Is that right? So xl squared upon 4, of course, which is, okay, let's just take out 12. So you will just have f upon 48 Young's modulus inertia, and then this is going to be 4 times that. So like negative 4x cubed plus 3xl squared. Awesome. Finally, we have the equation. Okay. Actually, you know what? No, I like this one better because taking the derivative of this guy is much easier. So yeah, that's our y value. And what do you want, by the way? Is that right? The y value? So 302. Oh, you want the deflection with the force at the middle of the grid. Oh, okay, fine. Just put x is equal to, okay, in that case, it might actually be better to factor out some more stuff. So it's going to be like fx upon, there was 48, of course. Just put that. So like 48 Young's modulus inertia. And you just got like negative 4x squared plus 3l squared. It's like 3l squared plus 4x squared, of course. Awesome. This is the thing. So I guess this is much more superior than that one. The last version. Yeah. Now just put x is equal to L upon 2 and let's see what happens. F L upon 2 is like for L upon 90. What is this? 96. Okay, that's interesting. And it's going to be 3L squared minus L squared. Oh, why did I do that 2 stuff in that case? Which is 48. L upon 2 and you're going to have what? 2L squared. So just L cube. That should be the thing. That's our deflection at the central point. Next question. 303. The thickness of rectangular steel girder equals h using the equation of problem 1.301. Find deflection caused by the weight of the girder in two cases. 301, which is what? 301 was, what kind of question was it? Oh, just this thing. Whatever. Right, like this, huh? No big deal. So 303, the thickness of the rectangular steel girder equals h using the equation of problem 1.301. Find the deflection caused by the weight of the girder. Oh god, no. I don't want to do that once again. Okay, fine. Weight. So one end of the girder is into wall with a length of the protruding length being equal to L. Hey, we just did the thing, right? Yeah, we did that for 300, except we actually didn't figure out the Y value. We should have done that. Ah, whatever. And girder of length 2L rests freely on two supports. You also have to figure that out. It's gonna take forever, right? Oh yeah, it is going to take forever, I guess. But hey, let's do it. 303. Let's do A. In both cases, we'll have to figure out something like that, right? Okay. Okay, interesting. Oh god. For the second case, it's much more complicated because like these two supports, you're gonna have forces acting on it and whatnot. I don't like the way it is going on. So I mean, okay, B is like if you're okay, so it's like the catenary problem, except that your wire has some kind of modulus of elasticity. This is very weird, but let's do it. A. One end of the girder is embedded in a wall. Okay, the problem that I did in my note, right? Let's do it once again. Yeah. So just do it right. Like tau is just equal to what? I, which is just equal to WH cube upon 12 times Young's modulus, and that times of what was the thing once again? Yeah, the curvature, which is like just y double dash actually. Now torque at some x, what's that going to be? It's got mg upon, okay, what's the mass by the way? Do we even know that? The area is, so the area is just rho times of w times. Okay, that's the area. That's rho is just the linear mass density. So this times of the remaining one, which is like L minus x, right? So this is the thing. It's at x and L minus x. Now you want this reacting at that point, right? Okay. This is going to be x plus L minus x upon 2. Or you could just say L minus x upon 2. Sorry. No, x plus L minus x upon. That's better. So L upon 2 minus x upon 2 plus x, which is L upon 2 plus x upon 2, right? This whole length just be L upon 2 plus x upon 2. Yeah, I guess so. So, which is making sense because this is just like L plus x upon 2, right? The average of this point and that point. So L plus, I should have done that already. Well, whatever. Yeah, so it's just this thing, L plus x upon 2. That's the something's really bad about this. It's not supposed to be like that. No, 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 no. We want the thing at this point. It's this length that we should look for, right? It's supposed to be L minus x and that thing upon 2, right? Not like this. Well, anyway, so that's our tau. This time's g, sorry. So, okay, L minus x, I just square off this guy actually. Yeah, but all of that times g and then upon 2. So, that's our torque. It's just equal to this guy. And now let's see. So some stuff should cancel out. This and then this is just one square. So rho L minus x squared g upon 2. Oh, that 2 just cancels by the way. It's just equal to, and then just put that 6 over here. And then you got Young's modulus h squared times y double dash. So our y double dash is just equal to 6 rho g upon Young's modulus h square, and that is that h square. Of course, it's h square. What else can it be? And then you got L minus x squared, right? Okay. Yeah, this is actually even more painful to do than the last one, but fine, we'll try it out. Y dash. Yeah, y dash is just equal to this constant, so 6 rho g upon Young's. You know what? Let's actually just figure out what the double integral of this thing is. Not worrying about this thing. So integrate that. You will just have L minus x, which is negative of that. L minus x cube upon 3 as it goes from x is equal to 0. At that point, y is also 0. So yeah, and then oh sorry, y dash is 0, sorry, and then till x. So you got L cube minus L minus x cube upon 3. Just rewrite it like that. Who cares? Yeah. Then you want to integrate this thing, so you're gonna have L cube upon 3 times of x, 0 to x, just that. Minus, yeah, you can see what's going to happen, right? It's like upon 12 and oof. And it's negative 7 minus x power 4 upon 12 as it goes from 0 to x. Cool. XL cube upon 3, then this thing is just going to be plus L minus x power 4 upon 12 and minus, so when you put x equal to 0, it's going to be L power 4 upon 12. What do you want, by the way? Actually, just give us the, yeah, I'm just going to give you the curve itself. We don't care about anything. Should I just keep it like that, or should I actually change this a bit? Starting to think maybe I should just keep it like that. No, I should write the polynomial equation. Maybe that's the better thing to do. So you got 1 upon 12, and then you got 4xl cubed, and yeah, I should have written it as an, oh god, I should have expanded this the first time I saw it. So skip all of that. We don't want to do this. Actually, now that we have it, why even do that? We'll just do this thing. Then you got minus L power 4 plus integration of this thing, which is, sorry, the expansion of this, which is like L power 4 minus 4L cube x plus 6L squared x squared minus 4LX cube plus x power 4. Some stuff cancels at least. This is over here. Yes. Just x power 4 minus 4L x cube plus 6L squared x squared. That's all that remains. So it's like x squared times of x squared minus 4LX squared plus 6L squared. Can we actually factorize? Oh, no, we can't, unfortunately. It's just 3 and 2. If this was 5 or something, could have been better, but we can't. But not yet, at least. Okay, so that's awesome. So you got this expression. And 1 upon 12 of that, of course. So this thing upon 12. This is what we should have put in that. So y is just equal to, and then 1 upon, okay, it's going to be upon 2. So rho g upon 2 y h squared, and put that in there. So it's x power, okay, x squared first of all. Yeah, oh, it's not supposed to be there. It was x cube or something. Uh-oh. Uh-oh. Was it x cube or not? What remained was this, oh yeah, it is x cube, sorry. So you don't have to do that. It's just x, by the way. This should be just x. Now, let's put that in there. The y is just equal to rho g upon 2 Young's modulus x squared times x squared minus 4lx plus 6l squared, right? That was the thing? Yeah. Of course it was the thing. Okay, you got the expression. So that is the thing, huh? Really. So A done. What do you want, by the way? Deflection lambda caused by the weight of the girder. Yeah, so lambda is just equal to, so when you put x is equal to L, you will get the thing. It will just be equal to rho g L power 4. We'll just have 1 minus 4 plus 6, I guess, which is 2. So that's there. I guess something went wrong. No, it's 3, sorry. Okay, 3 rho g L power 4 upon 2 Young's modulus h square. That's right. That's our lambda. Next question. Oh, and this y is not the Young's modulus, just equal to y. I should really use like something else, so z or something, right? Yeah, 304. Oh, okay, sorry. It should be B first. So B. The girder of length 2L rests freely on supports, figure 1. Oh, this is going to be so much more complicated, right? 1.78 B. Yeah, it's going to be so complicated. I don't even want to do this. Ah, okay, think about it. Once again, this is our origin, and then you got, okay, it's got some mass. So like its weight upon 2 is what we have the force over it, right? Right. Can it actually produce torques? So does this like, is this actually attached to, if it is attached, then you will be producing torque over there as well. If it's not, no need to worry. But is it? Is it? 304. No, it's like 303. Rest freely, then fine, cannot actually produce torques because it will be just having a contact force, right? It's the only normal force. Yeah. Okay. So no torque because of that contact. Cool. That's really the thing. So this complete length is just 2L, right? Okay. This is our x value. This is going to be 2L minus x. Right. Like half of that is what we should we even use this as our x value? Maybe, maybe not. Maybe not. What if we put, you know, this as the x equal to 0 point? So then you just got this as our x value. Then this will be L minus x, right? So there to there. Ah, you get the thing what I'm talking about. This thing, L minus x. This is L, of course. This L plus x is the complete thing. Right. At this particular point, with respect to this particular point, what's the torque? So you got the gravity acting, sure. You got this force, you got that force. Let's call this like W. This is W upon 2, and we'll figure out what W is, but later. First, just do this thing. Okay, so what's our tau? It is, so all the time we always take our uh, force to be like, sorry, our torque to be clockwise, right? So yeah, let's do the same thing over here as well, right? And if something does go wrong, we'll figure out the signs. So the clockwise one, this is actually anti-clockwise, is negative. Negative W upon 2 times L minus X. Okay, this one is also anti-clockwise. It's like, okay, that's also negative, negative W times of, oh, it's getting complicated. Your slope is actually increasing, right? So your y double dash is positive. So then this should also be positive in that case. We don't have to do that. Okay, it's just this. Oh, okay, that's fine. We'll do this first and then we'll think about it. So you got W font. Okay, that's the thing. And then W times of X, just X, sure. And the last one, so it's W upon 2 in that direction, so it's negative. Negative W upon 2 and just L plus X. Okay, which will be, so it's like L upon 2 minus X upon 2. That cancels. L upon 2 cancels. It's just negative. So like negative X upon 2, negative X upon 2, negative X. Just negative X over there. And this will be, oh god. Oh, this was to be expected. There is no torque. Wait, what? It doesn't feel correct about this one. Oh god. It's incorrect. This is not how it should be. We only need to think about the torque of one of the parts, not both the parts. That's why everything is going. I mean, of course, of the whole complete thing, you're gonna have torque equal to 0 because equilibrium. We just want this part, right? Not the complete. Okay, okay. I'm feeling really foolish right now. Whatever. It's pretty much the same stuff, right? You got L, you got M minus X. Ah, yeah. It's gonna be forever. Fine. This is X, you got M minus X. Now, You got W upon 2 force in this direction, and then there's this complete guy putting its own gravity, and oh my god. Hey, instead of writing W, it's gonna write it using density. So rho, this is just a width. You got G, all of that upon 2. For this, you got this force, which is how much? So like this, okay, minus x, fine. And how much is this force? It will be rho WH. It should have been this times of the length. That's better. Rho WH times L minus x times G, right? That's the force. Right. Now, this guy's distance from this is just L minus x upon 2. So, clockwise torques, right? Rho WH L minus x squared G upon 2. And this whole thing, and that's what distance is like L minus x, right? Okay. So, negative rho WH L times L minus x times G upon 2. Why is that upon 2? Oh, because of this one. Sure. So just equal to rho WH L minus x G, I think just, yeah, upon 2. And then you got L minus x minus L, I guess, which is just negative x. Cool. So just negative, or it should not be negative, right? Because our y is increasing, so it should be positive in that case. So rho x, that's L minus x. Actually, you know what? Just put every constant in the front. Rho WHG upon 2, and then you got x times of L minus x. That's the thing. That is our y, so our torque. So this torque is like equal to Young's modulus times IA, which just happens to be WH cube upon 12 times y double dash, or z double dash. I think we should use z double. From now on, we're going to use z, not y. But it will just like look not that aesthetic. Okay, this is our equation, so I'm going to use y. Fine, cancel out some stuff. This cancels, just h squared. This happens all of the times, right? Yeah. Whatever. It's just 6 rho g x times L minus x is equal to Young's modulus h squared times I, yeah, whatever, upon Young's modulus h squared equal to y double dash. So y double dash is just equal to 6 rho g upon Young's modulus h squared. And oh god, this times of this x times of L minus x. Wow, I'm starting to hate this thing a bit. So this thing Lx minus x squared. Now you will integrate this thing. Y dash is 0 at x equal to 0. So that's just perfect, right? It's going to be Lx of s squared upon 2 minus x cubed upon 3. And now bring that sixth thing inside. So it's rho g upon Young's modulus h squared. Then you got 3x squared L minus 2x cubed. Perfect. Now integrate this once again. So like y is just equal to rho g upon Young's modulus h squared. This is going to be what? Lx cube minus x power 4 upon 2 as it goes from something to something. Actually, this will be this plus some. Where is this 0, by the way? We don't know actually. Do we? Y is 0 at x is equal to L. So if we go from L to some other x, so at L it's 0, at x it's something, right? Then you just get y. Cool. So just put that in there. Rho g upon Young's modulus h squared, and then you got this lx cube minus x power 4 upon 2 minus L power 4 plus L power 4 upon 2. Perfect. Which is basically just minus L power 4 upon 2. Yeah, which can be thought of as like 2, oh sorry, not 2. Okay, rho g upon 2 Young's modulus h square. And then you're going to have this thing. 2lx cube minus x power 4 minus L power 4. Interesting. It's like this was meant to be factored out, but then somehow we cannot factor this out yet. Yeah. Well, whatever. That's the thing. So you got the y value. That's our curve. Now what do you want, by the way? Oh yeah, you want the deflection, of course. So our deflection is just... I might have messed up something. When we did the mass of the thing, so when we did the weight over there, that is not good. The weight is not just that. Shit. I messed up the whole derivation in that case. Because the weight, what I did for the weight was not what I should have done. Right? Oh, this is not nice. For weight, I didn't consider that factor of 2. It should have been like 2L WH rho. Oh god. Oh no. No, no, no. Oh. We need some other method that doesn't make me fall into these kind of traps, right? Yeah. Think about it. What kind of method would I use? So our equation for any, like, yeah, so this kind of problem, it has to do with rectangular cross sections all the time, right? So yeah, now I don't know, is there any better way for this? I have torque at some, right, you will have forces at some different points and whatnot. You can also consider like an extra force over here and just take that as x equal to 0, right? Sure. Let's write out a general equation, So yeah, such that you can do it. Now our tau thing, is that on this clockwise or anti-clockwise? Like the curvature. It was because of the torque, right? Yeah. So if you cut it like that and then it's like curving down because of this or something like that. So if this is the curving up, that means our torque should be up, right? So okay, like R 1 upon R. Okay, just y double dash. Y double dash. When is this going to be positive? When your thing is actually downward, right? Oh yeah, sure. So that your derivative increases. So whenever it's like downward, so for that to happen, of course, your torque should be clockwise. So that's why we take the clockwise ones to be positive, right? Okay. So what we are doing is figure out how to do it for general cases. See, this is our x equal to 0 point where it's pivoted. Now this is our length. We'll call this complete length as L. Okay. Right. Once again, the same kind of stuff. Our torque. How do we get that actually? You got this x equation. Okay. So this is x. This is L minus x. So you can have all of the torques that you usually have, but also have some extra stuff. Huh. Maybe x being length is not the best thing. What if we used something else? What if, say, x was a fraction, right? So it was the fraction of length. So this is L times x, and this would just be L times of 1 as x, right? Isn't that is better? I think so. I think so. So in that case, our y double dash, that would just become like, yeah, you're gonna have dx squared. So each of these times is L, and yeah. So our y double dash, that's actually that will get replaced by y double dash upon L squared, right? Yeah. So then our equation basically just becomes like tau times L squared is equal to IA Young's modulus and then y double dash. Right. So to figure out this torque, first of all, just put what IA is. It's just just WH cube upon 12 Young's modulus y double dash. Then you got this thing. Okay. So at some certain x, there's the torque because of its own weight. All of the time we're going to consider that. If somehow the weight is 0, this interval density to be 0, right? And then there's some extra forces that you also have to consider, right? Yeah. So the torque because of those forces, how would we do that one? Let's just say the forces are at some sort of x value. So x is equal to xi, or the thing, right? Then you just have like summation of fi, and all of these fi's, those will be in the clockwise sense, right? So yeah, I guess so. Like, okay, if that arm length is like positive, your fi should be downward. So your downward position will be positive. Okay, now it's at xi minus x, that's the arm length, right? Okay, interesting. So summation of fi times xi minus x. Oh, this comes of length, sorry, because now xi is not length anymore. Okay. So you want that to be there, cool. And all of the forces except, okay, even if you take that, doesn't really hurt because this guy's xi is 0, so, and of course, you only want to do this for this much of the thing. Okay, so this is the torque external. I'm saying external, but it's not really like that. It's just because of the external forces that we don't know how they're happening. And then there's gravity, which we know how it's working. Okay, so that's awesome. And torque, gravity, how we are going to do that? Like, okay. So it's this mass, right? The mass is just rho WH times this length, which is L times of 1 minus x. Okay. So this times g, that's our weight. This will be at L times of 1 minus x upon 2. That's our arm length, right? And it's just going down, so it's good. It's clockwise. Wow, it's getting complicated. I guess that's the correct thing. L times 1 minus x upon 2. Sure, what could go wrong? I don't think anything would go wrong. So this would just be equal to rho WHL squared g upon 2, and then you got 1 minus x squared. So I'm going to put that and that combined over there. We'll see what happens. It's just L cube, and then you got summation of fi times xi minus x plus some stuff like this, huh? Okay. Maybe we could say, okay, maybe like, okay, these forces are some fraction of weights. So Fi is equal to eta I times the weight. Does that make sense? Okay. And we know what the weight is. It's just equal to rho W HL G, right? So if I do that, then this whole equation will become a different thing than what we are doing. So this will just become what? summation of, you get some stuff out, but first rho WHL squared G, oh god, oh yeah, and that times of this thing, summation of eta I xi minus x. Okay, so just write down everything correctly now. You're gonna add these up. It is rho WHL squared G times 1 minus x squared upon 2 plus summation of eta I xi minus x. Okay, and this thing, this is our torque, that's just equal to this equation, right? Okay. Oh, and this times of L squared, by the way, because sure. So L power 4. That is equal to WH cube upon 12 Young's modulus y double dash. Perfect. Oh god, it's gonna take forever. Yeah, well, isn't that interesting? So from now on, I'll be using X for a different purpose altogether. So the last ones, you won't use that. Maybe I should do something else, like alpha, probably. Instead of X, I'm just going to use alpha. I could, right? Whatever. First of all, let's just see what happens. So y double dash is just equal to, oh, and sub of cancel, of course, like this cancels. I have x squared is equal to 6 rho L power 4 G, 6 rho G L power 4 basically, upon h squared Young's modulus h squared, and that 12 goes inside. Oh, sorry, the 2 of that 12 goes inside. Like just becomes 1 minus x squared plus 2 summation of eta I xi minus x. Isn't that is perfect now? I think so. Yeah, that must be perfect. Of course, what could go wrong? It has to be like that. Okay, that's what y double dash. Just write out completely. So I want to test out this thing, right? So you got y double dash. I mean, it looks good. I don't know if it actually is correct or not. So yeah. Or, you know, let's not say it's like y double, just say it's d square y upon, and now I'm going to use alpha because I want to keep x for length, right? I think that is the way it should be. Yeah, just keep it for length and don't worry so much. Huh, interesting. It's going to be this thing, 6 rho G L power 4 upon Young's modulus times h squared. You got this thing. So 1 is x squared plus summation 2 summation of eta I. Minimize a bit actually. Oh, it should be alpha, sorry. So 1 minus alpha squared plus 2 summation of eta I alpha I minus alpha. Perfect. And now let's use it to get something done. Let's just try another question, right? So, you know, before doing this question, like before doing B, we'll try A once again. So, right, and we'll see if this is actually the thing that I'm gonna get, right? Okay. So if I one end of the glider is embedded into the wall with length of the protruding section being equal to L, so it's like going out. In that case, your density is there. Your eta I is 0. I mean, there's no external force, so you don't have to consider this term. It is going to be this thing, d square y upon. Actually, no. I want to consider something where there is not. Okay, we'll see that. We'll do 2 questions. First, let's do this one. So this one, y upon d alpha square is just equal to this constant that times of 1 minus alpha squared, just that much, nothing else. And yeah, that should be the thing. Now we're gonna integrate this thing. So you just got dy upon d alpha, that is equal to 6 rho g l power 4 upon y h square, and then integrate that thing. Just, it's like what, negative 1 minus alpha power 3 upon 3. That cancels with this much, so I'm gonna have 2 over there. So forget about this 3 stuff, and then it goes something like 0 to alpha. So wow, it's taking forever. It's like 1 minus of 1 minus alpha cubed. That's this 1 minus 1 minus alpha cubed. Oh, okay. Now I'm not going to be fooled by that. We'll actually do it the proper way. We will expand this. So 1 minus 2 alpha plus alpha square, and then we'll integrate. Okay. Right. So alpha minus alpha squared plus alpha cube upon 3. That's what I get. So it's like what? 2 rho g l power 4 upon Young's modulus h squared times, okay, that 3 comes inside. Just get this thing, 3 alpha minus 3 alpha squared plus alpha cubed. Now integrate once again. So it just equal to 2 rho g I, okay, y is just equal to 2 rho g l power 4 upon Young's modulus h squared times, when you integrate, just get 3 alpha squared upon 2 minus alpha cubed plus alpha power 4 upon 4. So this will be what? That's like 3, and then minus that alpha, so just out, it's just 2 alpha, and then plus alpha squared upon 2 or something. So this will be like what? You can write it like this then, actually, rho g l power 4 upon 2 Young's modulus h squared, and then you got alpha squared times alpha powers, okay, alpha squared minus 4 alpha plus 6. Looks familiar, doesn't it? Yeah. Then distribute the L square things inside. So rho g upon 2 Young's modulus h squared. L squared times alpha squared, just x squared, and then L squared alpha squared, just once again x squared minus, you get the thing, right? xl plus 6l squared. And is that what I got? That equation? Where did I go? Yes, look at that. Just look at that. It's the same equation, isn't it? Yeah. So that confirms this equation, right? Yeah. So it's like a shortcut basically. Going to, yeah, okay. I should do that. There we go. Another useful equation, or hopefully useful, because I don't think I'm ever going to encounter these kind of questions ever again. Anyway, and let's do B now. So for B, actually, no, let's test out once again to see if there's need for this factor or not. So for, what was the question once again? Like this, right? No, not this. Oh, where did it go? 1.77. Right. A steel girder of length L rests freely on two supports. Actually, you know what? Let's use capital L and not small l, because I want to reserve small l for what they will assign us. Okay. So capital L will be the actual length, right? Yeah. Let's do it. So once again, what was I doing? Where did I go? Where did I go? Right. A steel girder of length L rests freely on two supports. The moment of inertia of the cross section is equal to I. So 1.77, this thing. Neglecting the mass of it. Oh god, okay, they gave us the I value, so you won't have the same thing. Ah, that is sad. Fine, so you can't use 302 to justify this constant. But whatever. We'll just do 304, sorry, 303b anyway. It's 2b now. So the girder of length 2L rests freely on two supports. 1.78b. What? Okay, yeah, that's the thing. Right, you want what, by the way? You want the deflection caused by the weight of the girder. Fine. Okay, let's do the thing. So this equation is going to become like, I'm just going to use y double dash, even though it's reserved for d squared y upon dx squared, but whatever. As long as we know the context, you can't get confused, right? It's equal to 6 rho g L power 4 upon Young's modulus. And L is just equal to 2 small l, by the way. Right? So I think we should use 2 small. Maybe not. I'm going to use that. So 2 power 4, which is 16 times 6. So 96 rho g. Oh, that's kind of weird. Okay, let's not jump to conclusions. First of all, let's just do this thing and then we'll figure out what's the thing. Okay. Right. In the end, after we have converted this to x, we'll do the actual thing. Right? After it's converted to x, we will use capital L is equal to 2 small l. And then we'll see what happens. So, what's our equation? 1 minus alpha power 2 plus 2. And now this summation, so you got so weight, and then that's just w upon 2, and this thing is also w upon 2, and you want at this, right? So this is the thing, right? Okay, awesome. Oh, okay, this weight is not supposed to be there. It's actually not part of the external force. This is the only external force. So on the supports, just wait a second. Okay, sorry, interruption. But anyway, you got w upon 2. So eta, that's going to be 1 upon 2, right? Okay, so eta is 1 upon 2, just 1 over there. And you got this thing, alpha I minus alpha. Right, so it's like this complete thing going on. Alpha minus alpha is just this part, right? Yeah, which is how much? It's just equal to 1 minus alpha, because alpha I is just 1 basically. So this will be 1 minus alpha at the end. Awesome. So it's like 1 minus alpha, and we got 1 minus alpha plus 1. Oh, sorry. We should have this downward. So actually, eta I will be negative 1 upon 2, not positive 1 upon 2. So it's supposed to be negative, right? This is the kind of expression. Yeah. That does it. I think, yeah, that's right. Can't go wrong. Sure. Right. So you got 1 minus alpha, and then you got 1 minus alpha minus 1, which is actually negative. Hey, it's the same thing as we got last time. But why? No, last time we didn't get, we had everything using L, right? It was L minus X, not capital L minus X that we got last time, right? So the last time equation, that was wrong. That was surely wrong. Fine, but now you got the correct thing. It's just equal to alpha minus negative alpha times 1 minus alpha, right? Which is basically like what? Negative alpha plus alpha squared, right? And this times this constant, 6 rho gl power 4 upon Young's modulus h squared. Sure, that makes sense. Right, downward is positive and upward is negative. Cool. So now, that's for y double dash. Just integrate this thing. Yeah, at alpha equal to 1 upon 2, you will have y dash being equal to 0, right? So y dash, as it goes from 1 upon 2 to alpha, right? That is only y dash basically. This is equal to, integrate this thing, and it goes from 1 upon 2 to alpha, right? First, just figure it out. So it's like negative alpha squared upon 2 plus alpha cube upon 3 as it goes from 1 upon 2 to alpha. At alpha is just this thing, alpha cube upon 3 minus alpha squared upon 2. At 1 upon 2, it's going to be what? Negative, negative, positive. 1 upon 2 squared, like 1 upon 8, okay. And then 1 upon 2 cube, oh, that's like 1 upon 8 already. But now it's negative, so negative 1 upon 24. This is like 2/3 of 1 upon 8. So, yeah, 3 minus, yeah, 2 upon 24, right? Which is just 1 upon 12. And, right, that's the thing. So, this expression, oh, by the way, you just want 6 times of that. Let's just put 12 times of that. So, like, you will have to put that thing, so 12 times of all of that, times rho g L power 4 upon 2h squared. We'll see what happens. This will just turn out to be what? 6 alpha cube minus, so you got 12 times. Okay. Oh, sorry, it should be 4. It should be 4 alpha cubed minus 6 alpha squared plus 1. Huh, looks familiar, doesn't it? But yeah, it's actually y dash, not y. Okay. And you got this thing, rho g L power 4 upon 2h squared. So our y value, that's actually going to be what? So at alpha equal to 0, it's just 0, right? That's awesome. That's one thing that will never change, because that's one of the supports that we're taking as x equal to 0, right? Okay. Or alpha equal to 0 or whatever. So just integrate this thing, just alpha power 4 minus 2 alpha cubed plus alpha, and this is just, yeah, rho g L power 4 upon 2x squared, which is, so take that alpha out, it's like alpha times alpha cube minus 2 alpha square plus 1. Interesting. And then you got, so L alpha will just be x. One of these L will actually be remaining. Oh, that's kind of weird. You know what? No, just bring everything inside. So bring that L power 4 inside. It will be x power 4 minus 2x cubed L plus xl cubed times rho g upon 2x squared. And now you can make capital L equal to 2 small l, that connection. So it will just be x power 4 minus 4x cubed plus what, 8 xl, oh god, it should be l over there, x cubed l, and then you got plus 8 xl cubed. Perfect. And all of that, what's happening, all of that times rho g upon 2h. That's the answer. Isn't that awesome? They got it much. Yeah, now this equation makes everything so much more clean. Oh, it's not y dash, sorry, it's equal to y. Sorry. Just everything. Delete everything. This is our y value. So you want what, by the way? You want lambda, which is at x is equal to L, right? Yeah. So a lambda will just be what? At x equal to L, just like L power 4 is common or whatever. It's 1 minus 4 plus 4, sorry, plus 8, which is 5. So it's like 5 rho g L power 4 upon 2 h squared. That should be a square. Why is that not? And where's the Young's modulus? Something's off about this. Okay, that's better. Much better. Cool. Yeah, I believe that's correct. Okay, so that's it. I'm completely tired now. So I'll see you in the next video. Bye.